Okay, we're continuing on here in the nuclear chemistry chapter. And last time you kind of got into kinetics, really, and kinetics of radioactive decay. And remember that when you're dealing with radioactive decay, really, it always follows what's referred to as first order kinetics. And as we saw last time, there's some special sort of formulas and symbols that sometimes people use for nuclear chemistry, but really it's still the same sort of first order kinetics that you dealt with in sort of regular chemical kinetics. That is the natural log of A is equal to the natural log of A naught minus KT. This A here is again kind of like your final concentration or amount. This is your initial. This is what is referred to as the decay constant in nuclear chemistry. It's equivalent to sort of the rate constant in sort of chemical kinetics. And a reminder here that T is time. This is sort of the concentration time dependency sort of equation. We also have a half-life equation that's specific for first order, which is the natural log of 2 divided by the decay constant. Now, a couple things that we talked about here. Typically, the decay constant will have units really of like 1 over some unit of time. So a lot of times it's 1 over seconds, reciprocal seconds, but it can be anything else like 1 over minutes, hours, days, weeks, years, whatever it may be. And that's really how you know it's first order. And in this case, that's typically what you have. As we talked about and as we did on a number of those sort of examples, very, very common that you have to use sort of both of these sort of equations together. And I would say, much like what we saw in some of those examples, you would obviously, in a lot of cases, kind of use the half-life equation here to solve for the decay constant. And once you have that, then you can kind of go back into this equation and really solve for whatever you may be looking for. So very, very common kind of using those formulas together. There are specific graphs that go with first order kinetics. The main one is the natural log of A versus time. That will give you a linear relationship where the slope of that line is equal to minus the decay constant. And that's because if you again rearrange the first order kinetics equation like so, that is basically it in a form of a straight line, y equals mx plus b. So again, graphed on the y is the natural log of A, graphed on the x is time. And that should yield you a straight line with a negatively sloping line. And that negatively sloping line will give you a negative slope along with these m is equal to negative k will turn your decay constant into a positive number, which is what it should be. Another sort of graph that's associated with first order is concentration versus time. It's not a linear relationship, but what it is it will start to decrease over time. Couple careful things to watch out for, obviously, as we talked about last time, if you use these equations. Unlike normal chemical kinetics, as we talked about, where we typically use molarity here on both sides, in sort of radioactive decay or nuclear chemistry, it really can be any units as long as they are the same units. So, for example, I think we had grams and grams or milligrams and milligrams. And also very common is it could be some type of rate of radioactive decay, like we saw, like counts per minute per gram of carbon. So again, it doesn't necessarily always be molarity in this sort of application, but they do definitely have to be the same units for everything to work out correctly. Speaking of the same units, the other really thing you do definitely want to watch out for are the units of time between these two. Again, this unit of time and the actual t does need to be the same units, and that's a very common mistake people make. They don't necessarily convert them to the same units, and really the time sort of aspect of that does not cancel out. Any questions on any of that stuff there that we talked about last time? Okay, then continuing on, we're going to talk a little about Where does the energy from a fission reaction occur? A fission reaction really could happen a couple ways. You could have a spontaneous fission reaction, and in sort of a spontaneous fission reaction, this isotope will break apart into two new isotopes. Usually will give off some neutrons and usually a lot of energy. So you can have sort of spontaneous fission where it just sort of breaks apart. You could also, as we'll talk a little bit about, kind of make it happen by shooting some type of particle at something that's stable that will then turn it into maybe something that's not so stable at this point that will go through fission and it will break apart again into two new nucleuses, some neutrons released, and also some energy. By the way, as we'll talk about, when it does this reaction, this fission reaction, you don't always get the same two products every single time. So there is some variations on what it would break apart into. Now, during the nuclear fission, some of the mass of the nucleus is actually converted into energy via Einstein's equation here. That's obviously not negative, so that's E equals mc squared. So equals mc squared. C being the speed of light here. And we could roll with the 3 times 10 to the 8 meters per second. The M here is mass, and more specifically in this sort of application, this M is what is referred to as the mass defect. And as we'll talk about, the mass defect is really that difference in the mass of sort of the particles that make up the nucleus and the mass of the nucleus itself, or the isotope itself. And it's that difference in mass that gets converted into energy. Each mole of uranium-238 that goes through fission will produce somewhere on the average of 1.7 times 10 to the 13 joules of energy being released. Again, if you compare that, as we talked about, to sort of a exothermic chemical reaction, you're only on the magnitude of like 10 to the 6. So you can see you get a lot more energy there that sort of comes out in a fission nuclear reaction than you do in some type of normal chemical exothermic reaction. Again, a reminder, we also talked about the difference between a chemical reaction and a nuclear reaction. In a chemical reaction, it's really just all about electrons and bonds breaking and making. We don't touch anything in the nucleus. That again is why we have conservation of the elements in that type of situation. In nuclear reactions, it's all about converting what's in the nucleus to different things, protons to neutrons, neutrons to protons. So we do not get that conservation of the elements like we talked about the other day. That's also why when we do balance a nuclear reaction, we don't do it traditionally like we balance a chemical equation by using coefficients, but we use mass numbers and atomic numbers on each side to balance them. So the mass defect and binding energy is when the nucleus forms, as I mentioned, some of the mass of the separate nucleons. Again, a reminder that nucleons are basically what makes up the nucleus. So that's basically like your mass number, your protons, and your neutrons. And so this is essentially what's in the nucleus. So basically your protons and your neutrons. And it's that sort of difference in mass that's converted into energy. And again, that mass difference is what is referred to as the mass defect. And the energy that is released when a nucleus forms is called the binding energy, or sometimes the nuclear binding energy. And there are a couple of conversions down here. And again, none of them are negative. 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules. 1 AMU of mass defect is 931 mega electron volts. So common units of binding energy are joules per nucleon, are mega electron volts per nucleon. And these are very common sort of units that are associated with binding energy. Now, we talked about stability as well. And binding energy per nucleon is another measure of stability. So the greater the binding energy per nucleon that you have, the more stable the nucleus is. So we can use binding energy as sort of a source of stability or measuring stability as well. Now, where these two numbers sort of come from, it does allow you to solve these problems a couple different ways. You could either use Einstein's equation to figure out the energy, or really these guys are sort of derived from that, or you could kind of just go in with the conversion sort of factors and kind of get yourself there as well. So I'll show you how to do it both ways, and you can kind of choose whichever way you want to do it. So let's take a look at an example. Let's say we had fluorine 19, and the nuclear binding energy, again, is the energy required to break up the nucleus into its components. So what we would want to figure out, for example, first off, in our fluorine 19, obviously here, we could go to the periodic table and see that our atomic number is 9. So fluorine 19 has 9 protons, and we take the mass number minus the atomic number will give us 10 neutrons. And remember that the mass defect is the difference between the mass of the protons and neutrons in the nucleus and the mass of the isotope. So in this particular case, fluorine 19 has an atomic mass of 18.9984 AMU. So the first thing I'm going to calculate is actually the mass defect. And again, that is the difference in the mass of those protons and neutrons and the mass of the isotope. So what I'm going to do is take my 9 protons and I'm going to multiply it by the atomic mass of a proton, which is this number right there, 1.007825 AMU. I am then going to add it to 10 times the mass of a neutron, which is right there. And as you remember, right, the neutron is the heaviest of those 3 particles, protons, electrons, and neutrons there. Mu. So this is basically the mass of our subatomic particles. I'm going to subtract that from the atomic mass of the isotope, which is 18.9984 AMU. And if I do that here, and go 9 times 1.007825 plus 10 times 1.008665, and then we're going to subtract 18.9984. So if you do that there, hopefully punch it in right, 0.158, we'll call it 7 AMU. This is the mass defect. This again is the difference between the mass of the isotope and the mass of the particles that make it up. And again, that is what's going to kind of be converted into energy through this process. So one way that you could calculate the binding energy is definitely you can use Einstein's equation. So to use Einstein's equation, we could take E is equal to mc squared. And again, we could put in there the m in this case is our mass defect that we just calculated. So 0.1587 AMU. We'll use our speed of light, which is 3 times 10 to the 8 meters per second squared. That's going to get me, I'm not going to use a rounded number on my calculator here. That's going to get me something with a lot of zeros. No, that's going to get me 4.760 times 10 to the 7. Now, in terms of the units here, we have AMU, meters squared, seconds squared. Now, an important relationship that you might remember is a joule is equal to a kilogram, meters squared, seconds squared. And that is what a joule is equal to. So we're really close to that type of value there. We have our meters squared and our seconds squared, but we have AMU here. So we can do a little conversion here 4.760 times 10 to the 7 AMU meters squared second squared divided by our friend 6.022 times 10 to the 26. 26 because 26 is kilograms. 23 is grams, right? So Avogadro's number to the 23rd is grams. Move it 3 places makes it kilograms, so it's 26. The AMU will cancel out here, and we will end up with 7.90 times 10 to the minus 20 joules. Remember that we oftentimes will give binding energy in units of joules per nucleon. And our nucleon here is 19. So we'll divide that by 19 nucleons. And we will end up with about 4.16 times 10 to the minus 21 joules per nucleon. First off, any questions on that calculation there? Now, I could at this point, if I wanted mega electron volts per nucleon, I could use one of those conversion factors. So for example, if I just want to turn this now into mega electron volts per nucleon, I could go with there are 1.602 times 10 minus 13 joules in a mega electron volt. So if I do that there and divide by 1.602 to the minus 13, let's see here. Come here. Let me just do a correction here. Well, I'm batting 1,000 this week on the calculator here. So let's try this again. All right, missed the squaring part. What are we gonna do? All right, let's try this again here. Do a little correction. So we can go 3 to the 8. I should square that. That's kind of what the formula says. 0.1587. That should actually get me up here 1.4283 times 10 to the 16. And pop that number into here. A little correction. That would then give me 1.4283 times 10 to the 16. And now I'm going to divide it by 6.022 to 26. And that will get me, let's see, that looks a little better, I think, 2.37 times 10 to the minus 11 joules. And divide that by 19. Gonna get me nowhere near that. Let's get rid of that. It says I edit this out in post-production here, and that's it here. All right, so we took 19. That get me 1.25, we'll call it, times 10 to the minus 12. Now let's see how we do at the end here. 1.602 to the minus 13. There we go. That looks much better. That gets us 7.792 mega electron volts per nucleon. So again, these are 2 different ways that you can display the answer. Don't forget the squaring part like myself there. Any questions on that there? All right, so what is sort of the alternative way you could do this? You can if you wanted to, once you got the mass defect, which is right there, you could actually just use those conversion factors that we saw in the previous slide where you don't have to necessarily use Einstein's equation. So you could take the AMU and you could take that 1 AMU is 931.5 mega electron volts and just go right into that. And you'll get 1.4783 mega electron volts. You could then divide it by 19 nucleon. And that'll get you essentially, with a little difference in rounding, basically the number we got on the bottom there, 7.780 mega electron volts per nucleon. You could obviously use the other conversion factor to convert it to joules that way. So you can go right into just using those conversions that we saw on the previous slide without having to use Einstein's equation, and you could kind of get yourself to the same answer. So it is your sort of preference, whichever way you want to go there. But any questions on that there? All right. So as I mentioned before, nuclear binding energy per nucleon is a way that you could look at stability. And as the binding energy per nucleon increases, so does the nuclear stability. And really right there, iron 56 is pretty much the highest, and binding energy per nucleon is pretty stable in that situation. And a lot will happen to kind of get you near that stability. Things kind of to the left of iron 56 will go through fusion type processes to try to get there. And fission processes have started to the right there. Fusion is the process under very extreme temperatures. Two small things make a larger nucleus put together. Fission is what we're talking about, where it separates out into two new nucleuses and gives off some neutrons. All right, so why don't you give it a go there and see what you come up with. We have, want the mass defect in mega electron volts per nucleon, and let's also do both, joules per nucleon as well. If it has a mass carbon-16 of 16.014701, the mass of a proton there, and a mass of a neutron, carbon number 6, I think. That's its number of protons there. So carbon here in this case, which is carbon-16, the protons we would have 6. Our neutrons would be 16 minus 6, which would be 10. That again is necessary to calculate the mass defect, so we'll do that first. Our mass defect in this case would be our 6 protons times the mass of a proton, 1.00783 AMU. We will add that to 10 times the mass of a neutron, 1.00866 AMU. We will subtract that from the atomic mass of the isotope, which is 16.014701 AMU. Again, that's going to give us our mass difference between our particles and the mass of the isotope that's going to be converted into energy. Try to punch in all the right numbers this time. All right, then minus 16.014701. Looks like we get a mass defect of 0.1189 AMU. Again, as I mentioned before, you do have a couple of options as to how you might want to approach it. You can use Einstein's equation, but once again, as I mentioned, you can use those sort of conversion factors, which are really based off of Einstein's equation. So I'm going to take that approach here. I'm going to go 0.1189, which is my mass defect. I'm going to convert it into mega electron volts by using that conversion. 1 AMU is 931.5 mega electron volts. That gets me, looks like 110.7 mega electron volts. We could divide it by our nucleons, which in this case is 16, protons and neutrons, really the mass number. And that's going to get me a 6.921 mega electron volts per nucleon. Since we're also looking for joules, we could convert that number there. into joules per nucleon by using our conversion factor. That 1 mega electron volt is 1.602 times 10 to the minus 13 joules. Mega electron volts would cancel, and you will end up with here, looks like 1.11 times 10 to the minus 12 joules per nucleon. So again, that is one approach and one way that you could take it. You also, again, could use, like we did before, Einstein's equation. And again, that should get you to sort of the similar sort of answer. So, for example, again, if you're going to go kind of the other way, E would be equal to 0.1189 AMU. 3 times 10 to the 8 meters per second squared. I'll try not to screw it up this time. There we go. 0.1189. Gets you 1.07 times 10 to the 16 AMU meters squared second squared. Once again, Avogadro's number to the 26 here to divide by. To bring that into kilograms and joules ultimately. Gets you 1.78 times 10 to the minus 11 joules divided by your 16 nucleons. And obviously, as you can see there, it gets you pretty much the same answer, 1.11 times 10 to the minus 12 joules per nucleon. Once again, you could convert it at that point to mega electron volts if you want to go sort of that route. So you could do either way, whichever way you're comfortable with. I imagine those two conversions will be provided for you, so maybe the conversion way might be a good way. Any questions on that there? All right, let's take a look at one last one here, I think. All right, calculate the binding energy per nucleon of iron 56. We'll just do it in mega electron volts per nucleon. That's good. Iron is 26 on the periodic table. Iron 26. That means here we got 26 protons, and in terms of neutrons, take our mass number 56, which is what that is, minus our atomic number of 26, which should be 30, I believe. So to calculate our mass defect here, we're going to go mass defect, going to be our 26 protons times the atomic mass there of a proton. We'll use that number there, 1.00783. 0.00783 AMU. We'll add it to 30 times our atomic mass of our neutron, same as last problem, 1.00866. 1.00866 AMU. We'll subtract it from the atomic mass here of our isotope. And gonna get us here 26 times 1.00783 plus 30 times 1.00866 minus 55.93494. Looks like 0.52844 AMUs are mass defect. What's going to be converted into energy. So we'll take that number and I'll just use the conversion. 1 AMU, 931.5 mega electron volts. Gives us 492.24 mega electron volts divided by really our mass number, which is our nucleons, which is 56. And that gets us basically an 8.790 mega electron volts per nucleon. Yeah. Any questions on that one there? Now, as we talked about before, this is a measure of stability. So if we just look at the ones we did, we had 6.921 for our carbon 16, 6.921 for our carbon 16. And we also had, what we did with there, the fluorine, I think it was. And for the fluorine there, we had on the previous page, 7.792. 7.792 mega electron volts per nucleon for our fluorine 19. So again, between carbon 16, fluorine 19, and our iron 56, we can see iron 56 here has a much higher binding energy per nucleon, which means it's much more stable than our fluorine, which is actually more stable than our carbon 16. Again, that is why we saw in that graph earlier. There it is right there at the top, iron 56, pretty much the most stable kind of isotope you could have there in terms of binding energy per nucleon. Any questions on how to calculate that? Okay. All right, here. All right, the next thing we're going to talk about is nuclear transmutation. So, as I mentioned before, you can't have spontaneous fission where it just sort of happens. You could also kind of help it along. And the way we form elements into other elements through transmutation, you could have sort of a particle accelerator. It's got a magnetic field, electrical field. And basically what happens is the particle gets moving pretty quick. And then it shoots at its sort of target. What happens typically if you shoot a particle at an isotope, it's not super happy, and a lot of times will become unstable and actually sort of split off and go through a fission type of reaction. That is how a lot of our sort of man-made elements are made, by basically shooting particles at stable nuclei that convert them. It's how we get our good guys like, californium, berkelium, einsteinium, and so forth. It's sometimes referred to as the transuranium elements. Those are the ones that are sort of made by man. And again, you can see shooting neutrons at particles, alpha particles will do that. And again, that's sort of how we bring together and make some of these new elements that are sort of created. The typical fission reaction in a sort of transmutation form is something like this. We have something like uranium-235, which is pretty happy. You shoot a neutron at it, it becomes a bowling pin and unhappy, and kind of splits off into two new nucleuses. It also gives off some neutrons in this process, and also a lot of energy, again, is sort of given off in this process. This is sort of the reaction that's used, for example, in a nuclear power plant as a fission reaction. Again, it generates a lot of energy through this process. Again, the comparison between uranium and a combustion of coal. It's uranium-235, you get like 10 to the 13 joules of energy per mole. Compare that to a ton of coal where you only get 10 to the 7 joules of energy. Again, you get a lot more energy there in the fission reaction than you do coal. Why do they compare it to coal? Because in a traditional power plant, they burn coal to use to basically power the plant. And obviously in like a nuclear power plant, they do a fission reaction to do so. So you get a lot more energy in that fission reaction than you do in the coal. As I mentioned before, there really is sort of not always going to get the same products as a result of a fission reaction. So even though we see here these two guys pop up, it doesn't mean that that is always what you will get when this fission reaction sort of occurs. There is sort of a high probability of guys that you might get in that region that typically pop up in these sort of fission reactions, but you may not always get the same two things. what you typically do usually get is the production of neutrons, and also the production of energy definitely occurs. So how does this reaction maybe not go crazy, or does kind of go out of control? If you let this fission reaction kind of go out of control, it is sometimes what is referred to as a nuclear chain reaction. And that's basically a self-sustaining part of a nuclear fission. And why does that happen? If you just think about the reaction we just saw, to sort of kick it off, you take a neutron and you shoot it at an isotope, basically. The result of that is it will split off into some new nucleuses and produce a bunch of neutrons, right? And since the neutrons are really the thing that starts the reaction, you're now kind of producing a lot more of the starting material, which can come back around and kind of start this whole process over again. And it can continue to sort of grow exponentially because of that, as you continuously sort of have this reaction occur, a lot more neutrons occur, keeps the reaction going. Obviously, every time it happens, it creates a lot of radioactive sort of particles and a lot of energy that happens on it. In order to have that reaction sort of continuously go, you need what is known as the critical mass of something like uranium. The critical mass is the minimum amount of mass that's needed basically to just let it keep going on. If you keep the critical mass below that, a non-critical mass, you won't have enough material to kind of keep this thing running and growing as fast, obviously, if you did. That's sort of the idea behind a sort of nuclear bomb, if you will. They have sort of a subcritical mass of uranium that end, a subcritical mass of uranium on the other end. And when this bomb hits, obviously it explodes, sends the wedge, if you will, into the pocket where it needs to be. The result of that is now when those two combine, you now have a critical mass of whatever that may be, and that's going to allow this sort of fission reaction to continue to go on, obviously producing a lot of radioactive fallout, a lot of energy going to be produced in that particular case. This fission reaction, as well, as I mentioned, is also what is used in a nuclear power plant. And any power plant, for the most part, simplified version of how it works is you have water, you heat the water. When you heat the water, you make steam. The steam is used to go out to the turbines, to the generators, and obviously you get some lights, right? And since this steam, you could kind of cool it back down in a nice circle and continue this process. So the difference between sort of a traditional power plant and a nuclear power plant is how they actually heat the water. In a traditional power plant, they burn coal to heat that water. In a nuclear power plant, they do a fission reaction to use the energy basically to heat the water to do so. So that's what we see here, nuclear power plant. Our closest one is out in San Onofre, although they're not really working, but that's where they're still sitting. They're off of the 5 freeway, right? It's the two big sort of towers that you come across. And there's usually a couple of parts. There's sort of the fission radioactive part, if you will. And then obviously here's our water. So what happens is they have fuel rods, and fuel rods are pretty much what they sound like. They're rods that have kind of like pencil eraser-sized pellets of uranium, and that is what kicks off basically the fission reaction. So as that fission reaction occurs in here, it will heat up the water that's in this tube. That heated water will come through the bigger thing of water, and obviously start to heat that. It allows the steam to make. The steam again will go out and sort of used for power. Usually nuclear power plants are situated near large bodies of water like the ocean, like we have in San Onofre for that same reason. They then can kind of cool down that steam back into water and have sort of a nice process that goes on. They try to keep obviously the radioactive part as separate as they can from the other part. But that's usually why they have those big sort of shields, if you will, containers over the entire thing. Now, why does this not go out of control when you do a fission reaction here in a nuclear power plant? They do have some control factors. Typically, they keep the mass as non-critical. So they try to not to have a critical mass of uranium to keep it going. They also have what are referred to as control rods. And control rods are things dipped in things like cadmium. Cadmium's a very good neutron absorber. And why would absorbing neutrons be really good in this situation? As we talked about a second ago, what kind of starts the reaction, kind of keeps the reaction going is those neutrons coming back around and sort of hitting the uranium. So if you have these control rods in there, they will start taking out some of the neutrons from the reaction and keep it under control and stuff like that. And again, that's why, for example, a nuclear power plant doesn't usually have too much issues in terms of the chain reaction occurring, unless you take out too many control rods at once, and then you get into some issues that can happen there. A lot of nuclear power plants are sort of decommissioned because it's too much money to keep them up and working. I think both of them I said are no free now, don't work, and I think they're going to try to decommission them, I think, if I saw recently. So what is the good and bad of both sort of power plants? Well, burning coal is not so great as well. It creates a lot of pollutants in the air. To get the coal, you got to do some things as well to the land. And obviously, nuclear power plants, although it's sort of cleaner than that, it obviously creates a lot of nuclear waste. And there's a lot of nuclear waste that are byproducts of the fission reaction, which are radioactive for a very, very long time. And for a very long time, they really didn't have anywhere to put it all because nobody wanted it to be moved across their town to go to a disposal site. So for a lot of years, the nuclear power plants would just store everything sort of on site. And eventually, though, they built something there in near Vegas, I think, in Nevada, big hole in the ground, and they started moving some stuff there. That is, how they keep the lights on there from all the glowing. This is what is sometimes referred to as spent fuel. And spent fuel is really the products of these fission reactions, which are also very much sort of alive and active for a long period of time. You can see here in terms of storage time, a lot of these products has to be stored for a lot of years. And that was also another key issue of what you do with this stuff, who keeps track of it, where do you put it for that many years until it's sort of not as bad, because obviously some of the spent fuel can be used for not good things if it is sort of not protected well. All right, nuclear fission on the other hand is a little bit different than nuclear fusion is a little bit different than nuclear fission. In fission, as we talked about, you can sort of split off one into two elements. In fusion, we basically take two smaller isotopes, put them together and make a larger one. And this is at really super high temperatures, like you're vacationing on the sun type temperatures. So very hot temperatures is what you're looking for there. That's why in all those movies, they want the guy that made like cold fusion. So you could kind of do that under normal conditions. We talked a little bit about it earlier as well in terms of half-lives, but a reminder that a lot of times radioisotopes are used in medicine, and obviously you're looking for probably a fairly short half-life. Otherwise, your follow-up appointment is going to be a really long time down the road. But you can see things like sodium-24, blood tracer, iodine-131 for your thyroid gland, technetium-99, some imaging. Radioactive isotopes and will basically behave the same way in your body as the non-radioactive isotope. The benefit of it is, besides the radioactivity, is you can kind of follow the radioactivity and it'll sort of highlight, obviously, in scans. And you can see what's going on in that type of situation. They also used to, a lot of times, they still do, I think, implant and like tumors and stuff, some radioactive pellets and stuff like that, try to shrink them. Here's a bone scan as well. As you can see, again, it's just going to highlight all those sort of areas. Now, this is a Geiger counter. If you ever use radioactivity, typically speaking, you should definitely make sure you understand what type of emitter it is, as they are different, an alpha emitter versus a beta versus a gamma. Gamma emitter goes very far into the skin. You need a lot more protection than if you're doing something with an alpha emitter. One of the things that's commonly used is a Geiger counter, and it's got a wand there and makes a little beeping noise, and you can use it to test for radioactivity. If it beeps really loud, then probably not so good. So usually you go around the spot where you're working and kind of Geiger counter everything, especially after you clean up as well, to make sure you didn't contaminate anything. You should always check your shoes as well, make sure you didn't step on anything, take anything home with you. Now, if I hold up a Geiger counter and just air, will it beep? The answer is yes. It hopefully shouldn't beep too loud, but it will do some beeping. And that is what is sometimes referred to as background radiation, as there is obviously background radiation a lot just around us. Here's where we get some radiation sort of doses, cosmic rays, ground and surroundings, X-rays, in case you're near a fallout of weapons testing or nuclear waste. You get these different ones. There is a RAD, which is a radiation absorbed dose, and there's a REM, which is the equivalent for man. And with the REM, they do sort of multiply it by a factor. Again, X-rays and beta particles go pretty far, so you need to have less exposure than something like alpha particles, which doesn't penetrate as far, so we have a little less of an exposure. Any questions on that? That's strawberries. Good deal on that. Any questions? All right, that wraps up chapter, whatever this was. All right, we got a few minutes. We will get into a little bit here of the next chapter, which is chapter 20. So chapter 20 is transition metals and coordination compounds. Also really the real last chapter we're probably going to maybe talk about, I think. So the first part of this chapter, we're going to talk about some reviews type stuff about transition metals that you should hopefully be familiar with. And then we'll get into really the heart of the chapter, which is about coordination chemistry, complex ions. So coming the first thing we're going to talk about is something known as effective nuclear charge. And this may be something that you are familiar with, but if not, then let's talk about it. So let's just take a really simple example of lithium, which is 1s2, 2s1 is its electron configuration. Lithium has one valence electron, which is this one here, and the 2s orbital. It has two lower energy electrons, which are known as core electrons, which are closer to the nucleus. So the idea of effective nuclear charge is this. If you take something like lithium's nucleus, it will have an overall positive 3 charge. And that obviously is because it has 3 protons in it. And if we just kind of line up the electrons here, and it's not perfect, but I'll just, for this picture's sake here, we have our lower energy electrons on our first energy level. On our second energy level, we got our valence electrons sort of happening out there. Now, when we think about the attraction of the electrons to the nucleus, it is really like an electrostatic attraction, positive, negative attractions together. And one of the ways that those are sort of stronger is if you have a higher sort of positive and negative charge, it will be held tighter than if you had a lower positive or negative charge. So what happens in this case is if we look at the lower energy electrons, they feel the full sort of brunt force there of the positive 3 attraction. So they're going to be held really, really tight, which is why they are the core electrons. Now, when we look at our lonely sort of valence electron over here, it is actually going to experience what is sometimes referred to as shielding. And the idea here is these electrons that are lower energy are actually going to shield that valence electron from the positive charge of the nucleus. And instead of it feeling the full brunt of the positive 3 charge, because these guys are sort of in the way, what ends up happening is they don't really get the full effect of it. And again, it's like if you went to the movies and you sat down dead center in the screen, and right before the movie starts, somebody sits right in front of me with a big giant hat, right? Blocks out half of the screen, shields half of the screen. Same idea here. So because of these lower energy electrons, it is not feeling that positive 3 charge. You can actually calculate the Z effective, which is really the charge it is feeling, by taking the positive charge of the nucleus minus the number of electrons that are shielding, which is 2. So what we see with our valence electron is instead of it feeling a +3 attraction to the nucleus, it's actually only feeling like a +1 attraction. So it's not going to be held as tightly. And as you know, that is one of the reasons why valence electrons are involved in bonding, right? Because they are furthest away from the nucleus, they're not held as tightly, and so forth. So in general, if you look at the periodic table, the Z effective increases as you go up and to the right and decreases as you go down to the left. Again, as you go to the right on the periodic table, the atomic number overall is increasing, which means that the number of protons are increasing, and then positive charge in the nucleus as you go to the right is actually increasing. So because it's starting with a greater positive charge, it's going to be able to pull in more of those electrons closer because it has that larger positive charge. And even those outer electrons will feel a little stronger of a pull towards the nucleus than somebody on the left that has a smaller number of protons in there to start with. And that's what we see here. If we look here, this is really period 3 on the periodic table. And as we go kind of across the periodic table, we see a greater effective nuclear charge. And we also see the result of that is atomic size gets smaller as you go to the right, because with those more protons, even those outer electrons will still feel a stronger pull than somebody to the right. And again, that's what we see here. Size gets smaller as you go to the right, up and to the right, and also that effective nuclear charge. Mainly, we're going to talk about in complex ions and coordination compounds, transition metals. And transition metals are, as you hopefully know, in this region of the periodic table. And a lot of complex ions basically will have transition metals in the center of them. And as you may also know, right, when we talk about transition metals, they are what are sometimes referred to as the D block on the periodic table. The first two groups are the S block. Groups 3 through 8 is the P block, and this is the F block over here. If you remember, S's have 2 electrons, right? 1 and 2. P subshell has 6 total, 1, 2, 3, 4, 5, and 6. D subshell has 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And F is 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. And again, you could count off electron configuration on the periodic table if you know what you're doing using the period numbers. The period numbers basically equals the N number, which is the principal quantum number, right? Is basically the energy level that's associated with it. Now, transition metals show great similarities within a given period. And within a group on the periodic table, they share very similar sort of properties. More than one oxidation state is oftentimes found, especially with transition metals, as you probably remember from naming. That is why we typically use Roman numerals, right, when we name a transition metal to indicate the positive charge that's on it. Cations and complex ions, again, are usually finds themselves with a transition metal in the middle and a number of ligands that are attached to it. Ligands, as we talked about in a previous chapter, are Lewis bases. And a reminder that a Lewis base is something that can donate a pair of electrons. So remember, when we talk about Lewis acids and bases, there's things that can donate a pair of electrons, Lewis bases. A Lewis acid, which is basically our metal ion here, is our Lewis acid. A Lewis acid is something that can accept a pair of electrons. And a cation that's in the middle, the only way it can become positively charged is it had to lose electrons, which means it's electron deficient, which means it's ready to accept electrons in that case. A lot of ligands, which are Lewis bases, will donate a pair of electrons. And those are things, for example, that are sometimes negatively charged because they have gained electrons. So they have electrons to give. And things that are polar molecules that have typically non-bonding electrons on the central atom, those are things that are good Lewis bases. And that's what we see in this picture. This is our cobalt, which again has a +3 charge. and that makes it very much electron deficient and a good Lewis acid. Ammonia here is our ligand in this case. And what is essentially happening here, if you look at ammonia, and you draw it better than I just did there. I don't want to, I want to double bond that for some reason, but I was trying not to. There we go. So if we draw ammonia here, it's a polar molecule. It has non-bonding electrons that is actually bringing in there and attaching to our cobalt here that makes our complex ion. You will, by the end of this chapter, know how to name that complex ion right there. You'll be able to call it hexamine cobalt 3 ion with no problem. And as we'll see in this chapter, naming these things sometimes takes an entire small way across the screen to come up with the name. Now, ionic compounds with transition metals, most compounds will have a colored sort of species as a result of transition metal and what light is being absorbed at a specific wavelength. Many compounds are paramagnetic. Paramagnetic means that you have unpaired electrons. Yeah, so unpaired electrons happening. Diamagnetic is they pair off each other, right? So we have unpaired electrons a lot of times in this. And a lot of things, as we'll talk about at the end of this chapter, which is a lot of times you are interested in maybe how many unpaired electrons a complex ion may have. Electron configurations is something that you do need to be able to write for transition metals and in general, because you will need to, in this chapter, figure out how many electrons something has in order to properly distribute the electrons. Just a quick reminder of electron configurations. There are s orbitals that could hold 2 electrons max. There are p subshells that could hold 6 electrons. And that's because each individual orbital could hold 2 electrons, right? And there's a px, py, and pz orbital, 3 different ones. 3 times 2 is 6. The d subshell has 5 orbitals. 5 times 2 is 10. And the f subshell has 14 electrons it could hold because it has 7 individual orbitals that each could hold 2. If you know that and you remember where each of these sort of orbitals start, like for example, on the S's, they start on the first energy level. On the P's, they show up on the second. The D's show up on the third. And the F's show up on the fourth. And if you just remember that and kind of write them diagonal to each other, you could then just fill in the numbers perhaps. 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 4f, 5f. And this is the proper order of electron configuration. You always start up here and you follow the arrows and sort of zigzag back and forth. So you start here and go this way, come back, come this way, come back, come this way, and you obviously would continue that process until you fill in all your electrons. As you may know, super commonly missed by a lot of people, after you go from the 3p, it's actually the 4s that's next, and back to the 3d. So when electrons go into the atom, the 4s electrons orbitals are lower in energy than the 3d. So electrons do fill in this order and go 4s and then into the 3d. What does happen though after you start putting the 3d in is there is a switch in energy, and the 4s actually becomes higher in energy than the 3d. And that's really important for when transition metals lose electrons. When transition metals lose electrons, they always lose the s's first, and then they go into the d's. There are some exceptions to the electron configuration that you may be aware of. Most people are told they need to know these two, which is chromium and copper. Chromium is number 24. It has 1 less electron in the s, 1 more electron in the d. Same thing with copper. What that essentially does is put an extra electron up in the d orbitals. So for chromium, it kind of fills an electron in a parallel spin, Hund's rule type situation. It makes it a little bit more stable. In copper, it will basically pair off that d and also make it more stable, because that 1s orbital will then be higher in energy and actually have an unpaired electron, which will make it a little bit more stable. By the way, just so you're familiar with, if you go to chromium and copper on the periodic table and you go down and in, a lot of those transition metals have very similar exceptions to their electron configuration. Something like PD, for example, has no electrons in the s. They've all gone up to the d. Silver also has a very similar sort of exception. This is also noble gas configuration, as hopefully you remember. It's a shorthand that you could write for electron configuration, where you put the noble gas that comes right before the element you're writing electron configuration for, and you put it in bracket, and then you just continue on with the